If you haven't already heard, our solar system is currently host to a strange and intriguing visitor. Comet 3I Atlas burst onto the astronomical scene in early July 2025, when it was first identified by the NASA-funded Atlas Survey Telescope, or Asteroid Terrestrial Impact Last Alert System, operating in Rio Utodo, Chile. Since then, scientists across the globe have assembled to collect every scrap of information they can get about this elusive entity, leading to a flurry of articles, alerts, papers, and controversies about the first interstellar object to enter our cosmic backyard in 6 years. But amid this media frenzy, what have we actually learned? What information about this comet is true, and what lies in the realms of science fiction? Join me in this video as I give you a much-needed update on 3I Atlas, piercing through the noise and getting to the heart of what makes this visitor so special, just in time for its 30th of October perihelion. Recap: 3I Atlas so far. If nothing else, the buzz around this comet proves how dynamic the world of science research can be. When I made my first video about 3I Atlas back in July, there were only around 4 published research papers naming it. Now, at the time of writing in September, there are nearly 70. That represents a huge number of new discoveries, verifications, and boosts in our collective knowledge about this object. But before I dive into the newest findings, let's do a quick recap of where we left off. In my previous video, I discussed the initial discovery of Comet 3I Atlas, named for its status as the third interstellar object to visit our solar system, and the Atlas Survey Telescope that identified it. I compared this comet to the famed Oumuamua, which made its way through our solar system in 2017, and Borisov, which was discovered in 2019. In contrast to its 2 interstellar predecessors, 3I Atlas is thought to be much faster, traveling at a whopping speed of 58 km per second, and older, with estimates that it is somewhere between 3 and 11 billion years old. That was a speedy summary, so you should definitely check out my first video, which you can watch at the link here, for more in-depth information. But since 3I Atlas made its debut on the channel, we have learned a lot more about it, thanks to countless hours of observation and measurements from astronomy facilities across the globe. So, what's the latest information to come from this researching spree? Images from Hubble. With the worldwide recognition that 3I Atlas has attracted since its discovery, it has managed to turn the heads of 2 very prestigious telescopes. It's famously difficult to schedule observation time with NASA's Hubble Space Telescope, with scientists having to submit proposals months in advance to argue their case for every minute of the telescope's time. But luckily for 3I Atlas, Hubble always reserves some time for so-called targets of opportunity, things that need to be observed before they move out of our reach, giving this unexpected interstellar visitor a free pass to skip the queue. And it was definitely worth it. Hubble captured this image of 3I Atlas on the 21st of July, when it was 446 million kilometers from Earth. You can get a sense of how fast the comet is traveling from the streaky stars in the background, and see the teardrop shape of the dust coming off its icy nucleus. These observations also allowed Hubble scientists to make estimates for the size of 3I Atlas's nucleus, measuring it between 440 m and 5.6 kilometers in diameter. That makes it a lot smaller than we originally thought, since original estimates of its size assumed that the comet's reflectance was coming entirely from the nucleus, not the coma. But now that the dust has cleared, we can see things in finer detail, and future observations may be able to pin down these measurements even more. Images from JWST. The other major player that has turned its attention to 3I Atlas is the James Webb Space Telescope. On the 6th of August, scientists used JWST's near-infrared spectrograph in an attempt to determine the composition of this comet, in a study led by astrochemist Dr. Martin Cordiner. They found a complex coma morphology, suggesting a range of different outgassing patterns depending on the elements and compounds being released. It seemed that carbon monoxide and carbon dioxide were sublimating more at this stage than water, but this is likely to change as the comet gets closer to the Sun. And while usually comet tails point away from the Sun, the researchers found a surprising amount of dust emanating from the comet in the direction of the Sun, caused by the dust grains fragmenting as they move further from the nucleus, and in turn, reflecting more light. This process might be exacerbated by gas production, as excessive carbon dioxide production could actually be launching the dust further away from the nucleus. Pretty dramatic for a feature that appears to us as nothing more than a hazy glow. TESS. Hubble and James Webb are not the only NASA telescopes getting in on the 3i Atlas fun. The Transiting Exoplanet Survey Satellite, affectionately known as TESS, has spent more than 7 years conducting an all-sky survey to discover exoplanets orbiting around nearby, bright stars. It uses 4 identical wide-field cameras to map the sky in 90 by 24 degree strips, and has already discovered thousands of planetary candidates. But as it turns out, TESS isn't just good at detecting exoplanets, but smaller objects too. Objects like comets. In my previous video, I mentioned that the first official discovery of 3i Atlas was actually predated by observations going back to June 14. However, astronomers working with NASA's TESS mission realized that they had observational data for this comet dated all the way back to May. The comet was captured by TESS from 7th of May to the 2nd of June, and was made visible in composite deep stack images. With this new data, astronomers had the chance to verify the earlier measurements made from 3i Atlas, and make some new discoveries of their own. In a paper published on the 11th of September, Odina Feinstein, John Noonan and Darrell Seligman used data from TESS to measure the brightness of 3i Atlas. They found that the average visual magnitude recorded by one of the TESS detectors was in line with previous estimates made by other astronomers using the same data. But the comet was about to defy expectations in another way. 3i Atlas got brighter. Between the 7th of May and the 2nd of June, the distance between 3i Atlas and the TESS spacecraft decreased by $0.90. From this change alone, the authors expected the object to get brighter, since it would be closer to the Sun and could reflect more of its light. They calculated that the comet's flux, or the amount of energy received from it, would increase by a factor of 1.5, corresponding to a magnitude of 20.5. But the object got much brighter than that. Its magnitude increased to 19.28. This shocking surge in brightness was the result of 3i Atlas increasing its flux by a factor of 5, not 1.5. Observations with the TRAPPIST North and South telescopes reported similar brightness values, confirming there was no miscalculation. With such a huge amount of energy radiating from this object, 3i Atlas is far more active than we originally thought, and may have been active for a long time. Combining their magnitude values with the Hubble estimates for nuclear size, the researchers found that 3i Atlas may have been active when it was still a whopping 6 astronomical units away from the Sun. That's near the outer limits of where comets usually start outgassing, suggesting that 3i Atlas might have been releasing something more exotic and hypervolatile at this time, like nitrogen or hydrogen. The comet's shape. In my previous video I said that 3i Atlas had a flatter light curve than Oumuamua, which suggests that it reflects light more evenly across its surface. Well, Feinstein and her colleagues came to a similar conclusion when they tried to extract a light curve for this comet using the TESS data. In fact, they struggled to find any patterns in the light curve at all, so they couldn't conclusively identify the comet's rotation period. They did identify some periodic signals, one every 29 hours and another every 16 hours, but the data was noisy, and TESS may not have been sensitive enough to measure this kind of parameter for a faint object like 3i Atlas. Luckily, other studies using specialized ground-based telescopes agree with the 16-hour spin period, so we can be more confident of the comet's shape and how it rotates. I've only covered space telescope discoveries so far, but discoveries about 3i Atlas have been made by telescopes back on Earth, too.